Hello, I'm Raul. I'm an assistant professor at the University of Chicago in the Department of Computer Science. And today I'll be telling you about data markets and how to protect those when there are strategic barriers. The background for this work is that the large increase in the demand for data has led to the appearance of a number of data markets. So when you think of systems like AWS Data Marketplace or Snowflake, or even Narrative, which is an up-and-coming company, they all list data sets that sellers have provided with the hope that some buyer who needs access to that data will be able to find it and pay for it. Now, all these data markets in their ideal form would be great in that they would unlock value for lots of people who do not have access to that data otherwise. But they have to solve a pretty hard problem, which is the pricing problem. How to come up with a price for the data sets that are listed. And so this is hard because if it's not set well, sellers might risk losing some revenue, potential money that they could have made had they priced the dataset higher. At the same time that buyers might risk overpaying if they don't know exactly what's the value of the dataset that they are obtaining. And the real challenge is that pricing data is actually quite hard. And this is for different reasons. The first one is that data can be used for many different reasons. Different people can have different use cases. So that's what we refer to as the combinatorial power of data. You combine it with another data set and suddenly the value changes, right? It's non-drivable, which means that multiple different parties can be using the same data set at the same time without having to pay more for that. And they don't have to pay more for that because it's also free to replicate. We can copy data at almost zero cost. So all of this introduces a bunch of challenges in terms of price and data sets. And what we're going to be looking into this talk is how, when we present a specific data market model, there'll be the need for addressing strategic buyers, people who are going to try to benefit from the way the market works. So this is roughly the outline of the talk, and I'll start directly by telling you more about the data market model, which is shown in this slide. In the middle, we have an arbiter that runs the data market. We have sellers on the right-hand side. These are people who own data sets and decide to list them in the market for sale. And then we have buyers that have some data need, and they express their willingness to access a specific data set by providing a bid. So here you see in the slide an example of buyer one sending a bid 1 with a value equals to 5. Now, this is a very abstract data market model, but it represents or it encompasses many different specific queries. So you can imagine how augmenting a table, for example, if you want to train a machine learning model, would be a model that could be laid on top of this one. And the same is true for data appends or segment lists, query to those products that data brokers sell. And similarly for table and content expansion, and there's really a number of queries that would fit well this model. Now, this data market model has a number of requirements. The arbiter wants to maximize revenue, and that is because it needs to raise money to compensate the sellers who are sharing those data sets. If it doesn't have enough money to compensate the sellers won't share. At the same time, because the reason that I mentioned earlier, which is that the same data set can be used for many different reasons, the market, the arbiter in this case, cannot really assume how much the buyers are going to be valuing data. So it's going to have to work with unknown value distributions. And then, of course, we want to make sure that when someone asks for a data set, we can sell that data set fairly fast. That's what I refer here as low latency pricing. So because we are going to be concentrating on strategic buyers, I will zoom in on the buyer model. I will explain how buyers would access this market. And so here we talk about a buyer I that wants to obtain data D to maximize the utility use of I. So the expression is shown here on the center of the slide, and I will unpack it. Has 3 terms. The first of which is the allocation function. So this function is going to take the value 1 if the bid that the buyer sent is higher than the price of the dataset D, which I'm going to be referring to on the slides as P of D at time T, and it'll be 0 otherwise. So what this means is that if I bid for a dataset and I don't get it, my utility will be 0. Now, if I did get the dataset, then the question is, what are the other factors that affect my utility? So this next term here shows the buyer's private valuation, which is represented with V sub I, and the price for the data. And so the difference between those two, how much I value the dataset and how much I pay, will contribute to my utility. Now, here we are going to assume that the buyer actually knows V sub I, which is realistic in scenarios such as someone can assign a specific business value to an increase of accuracy on a prediction. And so if a data set gives you that increase in the prediction, then you can value that. So what this term is saying then is that whatever is worth minus what I pay will contribute to my utility. And then the last term, quite important, is the deadline function, which I show here with delta. This will be 1 if we obtain the data set before a deadline tau sub I, and it'll be 0 otherwise. And this is essentially to model that certain buyers, if they had to wait too long to get access to a data set, they may as well just try to access the data set elsewhere and would not contribute to the data market activity. So we want to model that by including this deadline function. And so the intuition is, as I show here, if there's a number of times at which one can bid, as you see, the green box is a time at which the utility will be positive because it's before tau sub I, while the orange box, it's afterwards, and so it would make that function 0. I want to note before moving forward that there are 2 assumptions that I've made here in this buyer model, that V sub I is known. The paper will show a way in which we can extend it to cases where this is not known, and I'll say a little bit more about that later. And also the delta function takes a very specific shape, and that is not really necessary. It's just a way of simplifying the analysis in the presentation in this talk. Great, so the goal is that the arbiter, as I mentioned earlier, has to incentivize sellers to share. And so it's gonna have to take a look at those bids that are received from the buyers and identify a way of setting a price to the data with the goal of maximizing revenue. Now, the key challenge here is that because the buyers know that the price of the data depends on the bids, and they are the ones who are submitting the bids, they will envision ways of submitting those bids so as to maximize their utility. And so that's the key challenge that we want to address, that we address in this paper, and I'll give you a peek of at least some of the solutions that we have in the rest of the talk. So let me start with the intuition for one kind of attack that a buyer that knows how the market works could play out. So this buyer can bid at time T1 and T2, which I show here on this timeline. And so what the buyer will do is at time 1, it'll send a bid B sub 1 that is actually lower than its real valuation for that data set. And it's doing this with the hope that the market will check that bid and will adjust the price downward. Because if it does so, then when it's T equals 2, the buyer will send a second bid, B sub 2, which in this case is actually truthful. It represents its real valuation for that data set. Now, the crucial difference is that if the price was adjusted in between, then by submitting that B1 at the beginning, the buyer is moving the price in a profitable direction. Profitable in that it is maximizing its utility. So the idea that we have to protect against this specific attack, we call it epoch shield, and is that rather than the market adapting the price every bid, it'll adapt the price only after every epoch. So epoch is going to be a split of time. And so what it does mean is that for every epoch, we'll have a set of bids instead of only one. And so the market is going to have to envision a function, design a function, A of the vector B, as you see here, that will take the set of bids that arrive in an epoch and set the price that way. Now, when any function works, if we were to take a simple aggregate function such as an average or median, then the strategy from the perspective of the buyer is still clear. A low bid will drive the price down, will drive the average down or the median down. And so the key goal is to design that function A so that it's actually hard to gain, so that the buyer does not know what bid would influence that price significantly. The way we do that is we choose P of D, the price of the dataset, according to that expression that I showed there, which is really simple intuitively to understand if you look at the example that I have here. So we have the sequence of bids that are sorted, and we have the position of the bids that is indicated with K. And what we do is we find the bid that maximizes the K multiplied by B sub K over the sorted bids. And so this is essentially the expression that we typically use for choosing a posted price when we are thinking about posting pricing and an auction design. And so what's advantageous about choosing the price this way is that now if the buyer wants to modify that price, it has to essentially optimize a problem that is very hard for the buyer to do. So it'll have to find a bid such that the revenue that the market makes is larger, so that it actually wants to take that bid into consideration, at the same time that the price of the dataset goes down, because otherwise the buyer is really not getting anything in exchange. So what we saw is that with Epoch Sealed, we introduced this protection into the market, because now there is a collection of bits that the buyer would need to know about for it to be able to solve this optimization problem. So that might also give you an intuition on how, or what is the trade-off that this technique introduces. We call it the revenue protection trade-off. The larger the epoch size, the more bits will be inside, the higher the protection, but the lower the revenue. Now, let me show you one other strategy that buyers could use to strategize in the market. And so this is bidding over time, which, again, buyers can do because data is non-rival. So it could be used many times. It's not like we bid and we get it once and we cannot get it again. The data will remain in the market. And so what the buyer does here is that if it has a deadline tau sub I, it has a number of times where it can bid. It's going to use those number of times to create a sequence of strategic bids that will drive the price down. Similar to before, but now we are playing with the fact that we do have that specific set of periods to bid. The key idea of time shield, which is the protection mechanism we use, is that we make losing buyers wait, so they can only bid once more. If we did that, that would be great, because then if we only have one more chance to bid, you better bid your truthful bid, otherwise you will lose access to the data. And so you see here in the shaded area, the W sub I, which is the waiting period that we would assign to a losing buyer, so that they cannot bid much more than once more. Now, the challenge is that if we make honest loser buyers wait, we are harming their utility. And so we're going to have to choose W sub I in a way that disincentivizes strategic buyers, but without harming honest ones. And so that's the trick here. The way it works is a little bit involved, and the details are on the paper, but I wanted to give a little bit of the intuition. And the intuition is that the market is going to have to calculate the minimum time at which B sub I would be competitive. And the market is going to be able to do so because it knows the function that it's used to choose the price, the past bids, and the losing bid. And so it's going to be able to simulate a sequence of future bids that would make that bid that lost actually competitive. Another way of saying it is that the W sub I, the time period, is set up so that the buyer would not have been able to win the allocation earlier, no matter if even the original losing bid would have been truthful. Anyway, so the paper has a lot of other details. We talked about uncertainty seal, a technique for protecting against other kind of strategic behavior. We present an algorithm that puts all these three different techniques together. We have formal arguments for the claims that I've made earlier. And we also introduce an ex post mechanism, which is essentially breaking the assumption that V sub I is known a priori. So for example, we could support things like exploratory queries where you don't really know what the value of data is before you see the data. We have a pretty extensive experimental section as well. We show the strategic behavior with a real user study, and we use that same user study to show the effectiveness of the techniques that I gave you a taste for today. We also have a more sort of data-driven evaluation, more quantitative one, where we show what are the effects of the different protection techniques to the revenue of the market. To wrap up, I want to mention that when this paper was submitted, the reviewers commented that it wasn't clear that it was a good fit for Sigma. And so I wanted to reflect quickly on that and say that it is indeed true that it doesn't look like your typical VLDB, Sigma, or ICT paper, and the techniques are somewhat unusual as well. However, I think that because data markets are growing so fast, because of the existing models lack real details that I think would be important to tweak, and the data management community has much to contribute there. And because of our community is such a great nexus at bridging theory and practice, I think that it's important for people to think about these problems and sort of understand what are the other contributions that we could make in the field. So with that, I will stop here. I will offer a summary in the last slide. I've talked about the promise of data markets and extracting the value of data. How designing data markets is hard. I hopefully gave you a taste for some of the techniques that we've introduced to protect against strategic behavior. And I'll encourage you to reach out if you're interested in any of these problems.